So, ladies and gentlemen, welcome back from the lunch break. We'll get the afternoon session underway now with Piotr Głaska, who some of you may recognize. I'll hand you over. Piotr, all yours.
Thank you. Good afternoon, everybody. Thanks for coming up for dessert after the lunch. So for dessert, we have today the session how threat actors used and abused DNS protocol, DNS system. So we will have a look at real malware examples, and we will look just under one angle how the threat actor was using DNS during the attack. Not attacking DNS, but using DNS protocol, for example, within a ransomware, APT attacks, and so on. My name is Piotr. I'm based in Poland. I work for Infoblox, which is an American vendor of secure DNS solutions. That's why it's also actually not only my work, but also a passion to look how DNS is used by the threat actors and how it can be used for security purposes for defense. Small introduction, how basically DNS is used during the cyber kill chain. So how they are using DNS within each of phases of cyber kill chain. So there are the 7 phases of the attack, of targeted attack, and it starts with reconnaissance, right? Attacker tries to get as much information as possible about the victim, about the infrastructure, systems used, and so on. Usually they use DNS here to gather information about IP addressing, because in a DNS zone you have information about IP addresses. Very often you can find even private addressing then, because people which administer DNS, they do mistakes like every people do. So sometimes you can find even private IP addresses, you can find host names which can mean what kind of systems are used and so on. This information gathering could be passive through passive DNS systems. It could be active through DNS enumeration. But that's it. For the next phase, there is a weaponization. If they will use DNS, they need to usually register domains, set up authoritative DNS name servers, maybe put some code in the malware which will use DNS somehow, or buy such code. So that's the weaponization phase. They prepare the tools, the malicious content, which will be used later. Then we have delivery phase, where the actual malicious content is delivered to the victim. This can be done in many different ways, of course, right? Could be an email with attachment, could be an email with a link to a website with malicious content, so it could be indirect. Doesn't have to be an email, could be a message on LinkedIn from the headhunter, anything like that. If attackers will use some kind of link, it usually contains a domain name which needs to be resolved by the computer of the victim, right? So usually when people think about using DNS in the defense, they think about weaponizing, let's say, DNS resolver with a list of malicious domains, IP addresses, and the functionality to basically block resolution of such names. We will definitely not cover such basic scenarios today. We will look at the most advanced techniques used by the attackers. Then we have an exploitation phase. In the exploitation phase, attacker will try to exploit some vulnerabilities in the victim infrastructure or systems, processes, and so on. In terms of DNS, usually it's about exploiting vulnerabilities in DNS server software or in DNS client software. By DNS client, I mean this part of TCP/IP stack which is responsible for resolving name into the IP. And this is a code. This code is made by humans, so it also contains possible vulnerabilities. And I will show you one example. Then we have installation phase, where the malware is installed on the asset, and after that the malware will try to contact command and control server. So basically it needs to register itself, send some information, ask what to do next, send results of the executed tasks, and so on. To do that, basically IP address of the C2 server is needed. This IP address can be either hard-coded in the malware, which usually is the case in about 15% of malware cases. But more often it is stored as a fully qualified domain name, because if they store it as an IP and someone will notice the communication with this IP is suspicious, it will be blocked on the firewall, and that's the end of the story. So basically all the work done before is lost for them. So you always, advanced group especially, they will try to make some redundant ways how to connect to C2 server. Other ways they achieve that is maybe, for example, instead of hard coding domain name of the C2 server in the malware, for example, getting that domain name from some external service, usually legitimate one. For example, there are some malware families which are connecting to a legitimate cryptocurrency service, asking about how much money was spent from a specific crypto wallet, and this amount of money will determine which or what kind of domain will be generated. So anytime they need to change C2 domain name, they just reach out to this legitimate service, ask about the currency amount, and then use this amount to generate a new C2 domain. There are some other methods of generating domain names, from pseudo-random characters or words, and so on. After they know finally the IP address of the C2 server, there is communication happening between the infected host and the C2 server. This communication usually is using some typical popular protocols on the internet. And the most popular obviously are HTTP, HTTPS, mail protocols, and also DNS. DNS is probably one of the most popular and probably not that much inspected, right? Most security solutions are focusing on inspecting HTTP traffic, HTTPS traffic with decryption, mail traffic with mail gateways, but not too many solutions are focusing on inspecting DNS, which is a very popular protocol. So, one of the ways how attackers avoid detection is to use DNS as a command and control protocol. And this is done in form of sending DNS queries from infected host to the C2 server. And then the query itself, the name queried, contain encoded information. And then DNS reply from the C2 server can contain some data stored in different DNS records, TXT, but also A records or any other record. Finally, we have last phase, actions and objectives. Attacks are done for a purpose. It could be, for example, encrypting data and requesting ransom. It could be stealing sensitive information. It could be having an impact on business services. DNS is usually used for two things, either having an impact, because if DNS servers don't work, the network doesn't work. Internal DNS doesn't work, Active Directory doesn't work. External DNS doesn't work, external domain names doesn't work. So in case of bank, for example, bank services are not available. Or they can be used to steal information, because this information, the sensitive information, can be hidden inside of DNS query and sent through DNS servers towards C2 server. So that's an overview. Let's look at some real examples. First one, and we will start actually from quite advanced ones, and then I will show you more simpler. This one is was used by APT group called by Ukrainian cert UAC 0035. The malware is called Invisimal. This one, which you see, the screenshots of the attachment actually, which you see, were detected in March this year during the Russian invasion. So it was sent to one of the government officials. The attachment contained actually the link to get data from external service. And I will focus only on the DNS part here. The malware, the Invisimal, was seen also around 2 years ago, also attacking Ukrainian government institutions, military institutions. And they like to use DNS because when they attack such institutions, usually they have different segments of the networks. Some segments have internet connectivity, some don't have internet connectivity, and some are basically completely disconnected from any network. If they will infect some host in a segment which is, let's say, firewalled from the internet, right? So basically there is network connectivity, but there is no direct internet connection. For example, let's say this host cannot reach any internet IP addresses because basically several layers of firewalls are blocking this traffic. Still, very often there is possibility to connect with such host and communicate with it. So, for example, if this host gets infected and wants to connect to the C2 server, it can do it over DNS by sending a DNS query to local DNS resolver. So something like Microsoft DNS bind or whatever the victim is using. Then, because DNS as a protocol, it works as a proxy mechanism. So basically this resolver is not just forwarding the packets from client to the server. No, it is basically based on the client request. It is creating a new DNS query and it is sending it to the authoritative server, which in this case is controlled by the attacker. Then the server is responding, sending the reply to DNS resolver, and then this DNS resolver will supply DNS reply to the client. So basically, even though the client has no internet connection, it still can connect to internet, but to other hosts on the internet and have bidirectional communication. They used their very own DNS tunneling mechanism, so they didn't use any open source tools to do that. Basically, they write the code. It's an APT group backed by government, so they have time, money, resources to do that. They don't need to go the easy way. They encoded data in DNS query with base 32 encoding with custom alphabet, so it's not a standard base 32. And this is typical for APT groups. They will not use any simple encoding mechanisms such as base 64 or hex, which are widely available in the scripting languages. They usually use base 32 because of the characters which better fit DNS RFCs. And usually they will use custom alphabet, not a standard base 32 alphabet. Let's look at another example in more detail. Here we have an attack by APT34 group, which is Iranian APT group. And here we have example from this year of the attack targeting Jordanian government. There was an email sent to government official. The sender was pretending to be an IT employee. So basically first name, last name was of the real IT employee. Of course, the email itself was not proper one. It was some external outlook.com, I believe it was the domain. It was also interesting to see that how they send this email. You will not see it here, but the original email, which is quoted here, the original email was sent without attachment. So the email was saying, please fill the attached form, but actually there was no attachment and there was no link. So the email itself was not that suspicious because there was nothing which could harm the user. A few hours later, there was a second email to this employee, sorry, I forgot to attach attachment, right? So it was like pretending to do typical mistake in companies. Attachment was an Excel file, a malicious Excel file, which was containing Visual Basic macro. And interesting from my perspective, from DNS perspective, was that every major step in this macro was reported to C2 server via DNS query. So every time they achieve a major step in the macro, they send a DNS query to C2 server, which was basically very simple one saying, we are at phase 1, we are at phase 2, we are at phase 3. So if anything will go wrong, they know at which point defenders, for example, have stopped the actions. This is example of such DNS query. So basically, quite short one, not very suspicious. It was containing an ID of the step and some random number, because in case of DNS, you need to make sure that any query you send as an attacker cannot be answered from the cache by the local DNS resolver. Because if you get the answer from the cache, it means the query will not go further, will not go to the final authoritative DNS. So every query during DNS tunneling has to be unique. Also interesting was how they sent the DNS queries. Normally you use either NSLOOKUP or some kind of function or API request to resolve name to IP. In this case, though, they use, as you see, Win32 ping status function. Why they do that? Because sometimes some EDR systems might be counting how many queries is sending a specific process. If it's sending a lot of queries, it might be suspicious behavior, right? But if they do that, it's not that suspicious. And with every ping, actually there is a not with every ICMP packet, but with every call to this function, the resolving function will be used, because if you do like ping google.com, basically a DNS query is sent in the background. So this is how they avoid being detected by some functions of EDR. Also, there was an anti-sandbox function, a very simple one. Before the Excel was dropping malicious content to the disk, it would check if mouse is connected to this machine, because if there is no mouse, that's suspicious. Most likely the system is running in the sandbox. If there is a mouse connected, most likely it's not. But of course, it's just one of the methods. An Excel file contained a backdoor which was stored in an interesting way, because in the Excel there was a user form, so the form to be filled by user, and the name of the text field basically contained base64 encoded malware. So it was not very typical way to look for the malicious code. The backdoor itself finally was not run by the Excel, but it was written to the scheduler. So basically the scheduler would finally run the process, not the Excel itself, because again, that would be a little bit suspicious. About the backdoor, Saitama backdoor, which was dropped. So that was .NET binary, able to execute some pre-coded command, but also custom commands, and also able to download some new malicious plugins from the C2 server. By the way, some commands were, as I said, hard-coded, pre-coded, and these are examples of such commands. So you can see that they did some reconnaissance before, because the malware contained pre-coded information such as names of the servers to resolve, or IP addresses of the servers to check if the malware has connectivity to, for example. So definitely before this attack, they did some reconnaissance, they knew what are the important hosts, and it was hard-coded in the malware. Here we have example of C2 over DNS communication. So it doesn't look very suspicious. It's like not a very long query. They are changing domain names, so it's not like they sent a lot of queries to one domain. You have one domain here, another here, another here. They were using 3 domains, randomly choosing them with each query. It's not very long. It's even below average length of internet queries, so not too suspicious. Each query contains a counter. So here you see NRJ, NRC, NR6. That's a counter. The counter is used to, for example, check if all the queries reach the C2 server. It is also used to make the query unique, because it's a counter. It doesn't look like 1, 2, 3, 4, because it's actually base 36 encoded with custom alphabet. That's why it looks a little bit strange, let's say. But it is a counter. And this counter later is also used to encode the content. Each value of the counter is used to set up a table to transcode letters. So this is how they basically encoded the information in the C2 communication. Another example, Lyceum Group, also quite fresh from March. They were attacking, for example, Israeli companies, Israeli energy companies, and they were using topics such as Russian war crimes in Ukraine. So this is example email, and The key thing here is the link, which was used basically to download malicious Word document onto the computer of the victim. After opening this document, the macro would be dropping the malware in the startup folder. So basically, it will not run directly the malware, but after the computer is restarted, then the malware will be executed. And it was using, in similar way, C2 over DNS. This is how it was done. Actually, it could do C2 over DNS, but also over HTTP. So usually, really advanced groups, they will try to have a backup connectivity. If something will be blocked, they want to have additional methods. Like I said in the very beginning, they need to have ways to make sure connectivity will be achieved. This is also kind of a problem because C2 over DNS is different than C2 over HTTP. So how they make it easier for them? Basically, they send comments in the files, and they have just a file transmission method over DNS or over HTTP. So it was like 2 layers separated. They use A queries to exfiltrate data and TXT replies for command and control communication. Again, base 32 encoding with some custom alphabets like you see here. Normally, base 32 alphabet is like A, B, C, D, and so on. Here you can say it's completely different. Again, several domains used. And in this case, they were just a little bit simpler. They were using NSLOOKUP and DNS API calls to resolve domain names to IP addresses. So the before examples were quite advanced. Here we have an example of simple banking Trojan. Well, maybe not that simple, but a banking Trojan. So a malware which is attacking individual users, basically not very well defended, right? So one could expect it will use simple techniques. But in case of Flubot, actually, from a DNS perspective, they were quite advanced. Because what we can see here is they were using, for example, domain generation algorithm, DGA, to resolve C2 address to the IP address. For example, domain used by them could look like this one. So randomly selected characters, in this case in RU domain. So that was a domain created from, generated by some kind of algorithm they were using. So it is not easy to predict what would be the next domain, unless you know the algorithm. They were using, for example, command and control over DNS, but actually they were also using DNS over HTTPS. So it was C2 over DNS over HTTPS. Is it useful for the attackers? When attacking enterprise, not necessarily, depending on the configuration, but definitely, for example, if they attack individual user, which could potentially use some kind of secure DNS service, open source one, or like open resolver, or maybe their provider is providing something, then when they use DNS over HTTPS and connect to Google, DNS.Google or Cloudflare DNS, then basically they can bypass such secure DNS system. In enterprise, it's very easy to block actually, because it is enough to block on firewalls any IP packet to 8888 or 1111, and basically you are making unable such malware to communicate with DOH resolvers, most popular public DOH resolvers. So usually, if attackers are using DOH, it's rather in attacks against individual users or, let's say, simple targets. Base 32 encoding, completely untypical in such simple malware. Usually they would use hex or base 64. They were using base 64 to encode data in TXT replies. But I think it's a first simple malware which is using base 32, which I have seen so far in the last few years. Also, they were actually using encryption for command and control communication. So also not that typical for simple malware. Another example, this is a Linux backdoor called B1TXOR20, which is also using C2 over DNS. This one is exploiting log4j vulnerability. So basically it is scanning the network. If some hosts contain a vulnerable host, they will use this vulnerability to install the backdoor. The backdoor has possibility to basically execute commands, download new malicious plugins, install SOC 5 proxy. There was possibility to install a rootkit, exfiltrate data, those actions. And how communication was achieved here. So basic connection, the primary connection was a direct one, which means a malware will encode data. Before encoding, it would also compress the data, encrypt the data, then base 64 encode and send it as a DNS query, but directly priority one was a connection to public DNS, as you see. So Quad 8, so Google DNS. A little bit untypical because it was sent over TCP. Normally UDP protocol is used to send DNS queries. Here TCP was used. But anyway, this suggests that this malware is not targeting companies, it's not targeting enterprises, because in the enterprise, no host will have ability to contact basically external DNS services. There is a requirement that every computer on the network should use a local DNS. Port 53 is blocked, basically, on the firewalls. So if this is the first priority, it means this malware is not targeting companies, but rather individual users, maybe home routers, for example, because this is actually a Linux backdoor, right? So how many Linux computers are used at home? Rather, we talk about CCTV cameras or home routers, for example. There was some backup paths, so could be a direct connection over DNS to C2 server, which is also very untypical for, let's say, malware targeting companies. And as a third option, there was a backup to local DNS resolver. This method is typically used by attackers when they attack companies. They will use C2 over DNS by using local DNS resolver, most typically Microsoft DNS plus some bind servers. Sometimes DNS is used in a very simple way, but not the one which was designed for. For example, here we have example of malware which is distributed with cracked copies of some games, and they basically try to use hacked computers to mine cryptocurrency. They were quite successful with that because they mined at least $2 million. And how they use DNS here? If the malware want to check if there is a new malicious, if there is a new version of this malware basically on the C2 server, it needed again information about IP address of this server and what's the new version, if there is a new version. So how they did that? They were asking about such DNS entry, TXT record type, and in the TXT reply they had an IP address, but as you see it was encoded, so it was not normal use of DNS where you ask about an A record and you get an IP address. Here they ask about TXT record, and in this TXT record they have an IP address encoded, port on these servers to connect to, and also the version, the current version of the malware on this server. So they were asking about this record regularly just to check if there is a new version. If there is, they were connecting to this server, to this port, and downloading new malware. Also interesting case, not maybe from DNS perspective actually, but the first malware was seen which was targeting AWS Lambda serverless functionality. This malware was written in Go. It was used again to mine cryptocurrency on Lambda instances, and to avoid using local DNS resolver in AWS, which could potentially block something, they were using DOH or DNS over HTTPS to resolve C2 domain by using Google Resolver. Google Resolver is completely insecure. Basically, it will resolve anything. So that's why attackers like to use it, because then they can be sure that the domain name will be resolved to an IP address. Google doesn't block anything. So this is how they were resolving C2 domain name. Connection over HTTPS, dnsgoogle.com/resolve. So basically this is DOH protocol. And then you have a C2 domain name and the query type. They were also using the second, also very popular open resolver from Cloudflare. Basically, attackers like to use those because every Google Chrome, every Mozilla Firefox will issue a lot of queries over DOH. They will try to connect to Google, to Cloudflare DNS over DOH and start resolving DNS using those functionalities. So in your networks, basically you will see a lot of communication or communication attempts to Cloudflare DNS and to Google DNS. So if you see that, it's not suspicious, right? Which means it's a perfect way for the attacker. Another interesting use case, it's dependency confusion. Mr. Alex Birsan, I believe it was this year, beginning of this year or end of last year, he did interesting research regarding how software packages are downloaded by software developing tools. Because developers like to reuse software modules written by them or by anybody else. So when they create their code, they reuse different software modules written, for example, by someone else. And those modules are downloaded from software repositories, either private one of the company or the public one. And Alex basically discovered that the way how decision is made from where to get the software module is not very clear. And sometimes the software will actually reach first to the public repository to get the module. So if you put a module in the public repository, which will have the same name as the one in the private repository of the company, you have a big chance that your code will be used by the developer. So he did some research, get the names of the packages used by some companies such as Microsoft, Netflix, PayPal, Uber, and so on, which was not very hard because those names could be found in the public web pages. And then he put his code in public repositories under the same names. To get information that his code was run in these companies, he put a small code which would exfiltrate over DNS information about current working directory, operating system, user which executed the code, some very basic information. And then he put those packages in public software repositories. And he discovered that basically in every company which he tested, he was able to execute his code because he got those DNS queries coming very deep from their networks. Because usually, this code is executed somewhere behind several layers of firewalls. But it was still able to exfiltrate the information from this host because it was sent over DNS thanks to many DNS resolvers on the way. After that, some companies start to research even more. And for example, JFrog did some scanning of Python repository, and they found a lot of malicious modules. And here are some examples which are using DNS, for example, PPT test module. You can also note the version, 99 something. Why is that? Because, again, when a decision is made to get the software package from public or from private repository, the versions are compared as well. And the newest version is downloaded. So if you put in the public repository version like 999 or 9999, you have a bigger chance that your code will be actually pulled and executed. And here, those examples also were using DNS for some data exfiltration over DNS. For example, this one is similar to what Alex did, exfiltrating hostname, current working directory, local IP address. And finally, Last example, it's from exploitation phase. So I told you that there is possibility sometimes to exploit also DNS client software, and this is example of such vulnerability. Infrahalt, but actually in last 2 years there were many such vulnerabilities, at least 3 last year, 2 years ago, and they were very much the same. This one is from niche stack, a TCP/IP stack which is used commonly with Siemens S7 programmable logic controller. So a little bit topic better for tomorrow, to be honest, because it's about OT devices, IoT devices. And the quality of the code in such TCP/IP stacks is very, very low. So for example, if your computer is sending a DNS query to DNS server, it will first randomly select a UDP port from which to send the packet. It will randomly generate a transaction ID, 16-bit number of DNS transaction, and then will send this packet to the IP of a DNS server. When the reply comes back, of course, it should be coming back from the same IP of the server, should be coming to the same UDP port from which you send it, and the transaction ID should match. And guess what? In this case, in this stack, transaction ID is not randomly generated, UDP port is not randomly selected, and the IP address of the server is not checked at all when the reply comes back. So here you have a screenshot from POC where this device was tested, 1.21, and it is sending a DNS query to 8008, that's the server. Then the reply comes back from a completely different IP address. And even though it's a completely different IP address and should be ignored, basically, it is actually accepted, processed. The exploit, basically, it's using some vulnerability to execute a code on this device. And then an FTP session is started because that was the task of this POC. So wherever you have in your network, OT devices, IoT devices, basically make sure that they are really disconnected from the internet, and never forget about checking if they can send a DNS query about internet domain name. Because if they can, they will get the answer. It means there is bidirectional communication through DNS resolver, and this is often overlooked. Okay, that's it from my side. Maybe you have some questions.
Do we have any questions for Piotr? Are we there with the mic?
There's a question there.
Thank you for the talk. You told us some examples told about some examples of malware that use DNS over HTTPS, and there is technology of domain fronting, and it uses basically the same infrastructure, Cloudflare, Microsoft, and blah blah blah. But it is harder to detect this abuse because you need to break the SSL chain.
Yeah, correct. So domain front, the question was about domain fronting, right? That you can have a DNS query about one domain, but actually later in HTTP, which would be running under TLS as well, you have a different hostname, right?
Yeah.
And it was a huge issue maybe 2 years ago, because actually you could do that with Google DNS, for example. You connect to theoretically Google DNS, but then you have an HTTPS connection and request other hostname. But main cloud vendors have fixed that. And for Cloudflare, you cannot do domain fronting right now with their DNS servers. With Google also, you cannot. Of course, there will be for sure some vendors, some providers which can still be exploited in this way, let's say. And there is no easy way, because then, as you said, it is like you need to go and look what's in the decrypted packet, right? Because otherwise you cannot see. But for now, you cannot do it with, for example, Google DNS, because they fixed it, I believe it was 2 years ago. Huh?
So thank you.
World is a little bit safer thanks to that. because it was disaster. I mean, if you have situation like every computer on your network is connecting to DNS.Google and you don't know what is doing actually behind, right? So it's not nice. Any more questions? If not, then if you like the session and you would like to learn more, we are doing such training for about 6 hours. It's a free training. Here's the agenda. If you are interested, just come to Infoblox booth, leave your email, and we can set up such training either for your company, or if you are a student or maybe smaller company, then we can have a bigger session and we can do such training online. Thank you. That's it for now.
Piotr, thank you very much.